You have an industrial-scale solar array baking in direct, cloudless sunlight. Conditions are perfect, but down at the main inverter, the power output has stalled. The immediate reaction is panic. When thousands of watts disappear from the monitor, the natural assumption is that a piece of rooftop hardware has failed. These modules are engineered for 25 years of continuous exposure to the elements. Before writing off the hardware, we have to look for the failure points hidden between the sun and the inverter. Identifying the culprit requires a systematic troubleshooting approach, eliminating variables one by one rather than assuming the worst. We start our diagnostic funnel at the outermost layer, the physical surface of the glass. The most common causes of power loss are simple physical obstructions, like accumulated dust, mud, or bird droppings. This split-screen graphic compares the energy output of a clean panel with a soiled one. Even a thin layer of debris acts as a physical barrier, blocking photons from reaching the active cells and creating a disproportionate drop in total array output. The same rule applies to partial shading. A shadow from a single nearby tree branch or utility pole can choke the current flow and reduce the production of an entire string of connected panels. Then we have the heat paradox. While solar panels require direct sunlight to function, extremely hot, sunny days actually lower their operational efficiency. This chart shows ambient temperature across the bottom and voltage output on the side. As the physical heat of the solar array climbs, the electrical voltage of the modules predictably drops. Sunlight intensity, physical shadows, and ambient heat are the first variables to verify before we ever touch a piece of hardware. If the environment is clear and temperatures are normal, we shift our focus to the physical structure of the solar panel itself. Physical trauma doesn't always result in shattered glass. Serious defects like microcracks and delamination hide deep within the silicon layers, invisible to the naked eye. Looking at this schematic of a solar cell grid, we can see exactly how these microscopic fractures alter the internal electricity. The current flows normally until it hits a microcrack, creating a hard electrical bottleneck and bringing the flow to a halt. Weatherproofing can also fail. A damaged backsheet or a cracked seam allows rainwater to infiltrate the aluminum frame, destroying the internal circuitry through rapid corrosion. A panel that looks pristine from 20 feet away can still have a physical structure that has been compromised internally. When both the environment and the physical structure check out, we have to look underneath the array at the hidden electrical routing. MC4 connectors serve as the critical electrical bridges linking the separate solar panels into one continuous array. Because they handle high continuous loads outdoors, they are highly vulnerable. In this MC4 cross-section, standard energy flow hits a poorly crimped joint. Corrosion creates resistance, restricting current and radiating heat. Following the cables down, UV degradation or rodent bites strip away protective insulation. This damage bleeds energy, causing steep voltage drops. Right on the back of the panel is the junction box. This houses the bypass diodes, which act as the safety valves for the panel's internal power routing. If a bypass diode fails, it acts as a hard roadblock for that specific section of the module. This disrupts the output so severely that it often triggers a system-wide error code at the inverter. Trace the circuit from source to load. What looks like a dead panel is often a healthy solar cell trapped behind a broken electrical chain. Knowing the failure points in theory allows us to diagnose them systematically in the field. This technical inspection checklist dictates the diagnostic order. We start by reading the inverter error codes, look for physical shade or dirt on the glass, inspect the integrity of the MC4 connectors, and finally measure the string voltage to locate the fault. But any physical inspection carries lethal risk. Solar DC lines are dangerous. Even when the main system breaker is flipped off, a panel sitting in the sun is actively generating live voltage. You must use properly rated personal protective equipment and electrically insulated tools before attempting any physical fixes on a live array. A sudden loss of power is a mandate for methodical troubleshooting. Test the environment, check the hardware, and trace the electrical path before you write off the system.